the elementary particles census. Today, we're diving headfirst into this absolutely mind-bending cosmic audit from Quantum magazine to figure out exactly how many fundamental building blocks truly make up our universe. You know, whenever we hear about particle physics, there's always this underlying assumption that we've got it all figured out, that we know the exact number of ingredients in reality's recipe. Well, today, we're actually going to count them. But fair warning here, the deeper we go into this census, the weirder the math gets, and our whole understanding of reality, it really starts to fracture.
So, how many elementary particles are there? Let's dive right into this seemingly simple question. Physicists usually try to answer this using two main tools. First, you've got the incredibly precise mathematical equations of the Standard Model. And second, the mind-boggling, high-energy collision experiments happening over at the Large Hadron Collider. Because we can both theoretically describe and actually observe these little elementary bits and pieces, you'd naturally think, hey, we can just count them up, right? Well, actually, the answer to this question depends entirely on your personal appetite for complexity.
17. If you look at posters on a physics classroom wall, this is the comfortable, universally accepted baseline answer you're going to see. 17 particles. It feels super clean, right? It's manageable. You can fit the whole shebang neatly onto a single infographic. And honestly, for a lot of everyday physicists, this is exactly where the counting should begin and end.
Let's look at the classic Standard Model. Notice how neatly these 17 familiar particles are categorized. You've got your 12 fermions. Think of these as the tangible building blocks of matter, stuff like electrons, neutrinos, and quarks. Then you have your 4 bosons. These act as the messengers carrying the fundamental forces of nature, like the photon does for electromagnetism. And finally, sitting all by itself in a category of its own, is the Higgs boson, which basically gives other particles their mass. This right here is exactly where Harvard physicist Melissa Franklin says the count should absolutely 100% stop. But as you'll see, nature just loves a hidden layer.
And here is where we peel back the very first layer of nuance: antimatter perspectives, functional equivalence, or undeniably distinct. See, for every matter particle, there's an antiparticle with the exact opposite electric charge. Some physicists, like Franklin, just ignore antiparticles in the final census. Why? Because mathematically, they more or less just mirror their particle versions. It's kind of like they're just particles moving backward in time. But others push back and argue they are undeniably distinct. I mean, if antimatter touches matter, they literally annihilate each other upon contact. They play a totally different role in our reality, so shouldn't we count them?
30. By simply adding in those 12 antiparticles, plus the negatively charged version of the W boson, our cosmic tally suddenly leaps from 17 straight up to 30. Now, we haven't actually discovered anything new in the universe here. We've just decided to be a little more meticulous with our bookkeeping. But hold on, because we are really just getting started.
So what happens when we look at the forces holding everything together? Take the strong force, for example. The force-carrying gluons aren't just a single uniform particle. They actually possess these hidden variations, known as color charge. Now, the strong force is what binds the nucleus of an atom together, and it relies on a fundamental property that physicists casually call color, specifically red, green, and blue, along with their respective anticolors.
37. Because the strong force is actually conveyed by 8 mathematically distinct gluons that blend these colors and anticolors in really unique ways, our count jumps again. Even though an experimentalist can't easily distinguish these 8 gluons from one another in a lab setting, the mathematical equations that define the Standard Model treat them as entirely separate entities. So, just by properly counting the gluons, we're now sitting at 37 particles.
Just as red, green, and blue light blend to make white, colored quarks combine to form color-neutral protons. This brilliantly illustrates how quarks also utilize these color charges to create stable, isolated matter in our universe. Quarks come in these exact same 3 colors. But for matter to exist stably in isolation, it actually has to be color-neutral. Just like red, green, and blue light blend together to make white light, red, green, and blue quarks bind together to form color-neutral protons and neutrons. It's like a giant cosmic puzzle.
61. When we apply this logic and account for the 36 total color and anti-color combinations of all the quarks, the universe's inventory gets a whole lot more crowded. We have just skyrocketed to 61 fundamental elements. And remember, we are still talking about the exact same foundational building blocks. We're just zooming in closer and seeing how they splinter into totally different states.
Now let's talk about chirality.
This is basically a quantum version of handedness, where particles exist in mathematically distinct left-handed or right-handed mirror states. The crucial point here is that matter splinters into these left and right-handed varieties. Mathematically, these states are perfect mirror images of one another. You can't just, rotate a left-handed particle to make it right-handed. It just doesn't work. Fermilab physicist Chris Quigg insists we absolutely must count these separately.
Why chirality matters. This isn't just some arbitrary bookkeeping exercise. It fundamentally affects how particles behave and interact. These handedness and polarization states dictate physical interactions in nature. Take the weak force, for example, the one responsible for radioactive decay. It has a super strict rule. It only affects left-handed matter particles, period. No exceptions. And neutrinos? They only ever appear in a left-handed form in the standard model. Plus, force carriers have a very similar variation called polarization, left, right, and longitudinal. These are completely, physically distinct roles in reality. 118. By properly tallying every single chiral and polarization state, from a right-handed anti-charm quark all the way to a longitudinal W boson, we blast right past the 100 mark, landing at 118 elementary particles. For a lot of really detail-oriented physicists, this right here is the absolute maximum, rock-bottom number of particles you can possibly pull out of the standard model.
I think the true answer to your question is not an integer. That's a quote from Cambridge physicist David Tong. Right when you think the counting is finally over, Tong pulls the rug out from under us with this incredible physics-bending pivot. He argues that the true answer to how many particles exist isn't even a whole number. I mean, think about that. How could a particle count possibly be a fraction? Well, to understand this, we actually have to completely rethink what we are counting in the first place.
This brings us to degrees of freedom. Instead of counting distinct physical objects, quantum physicists count degrees of freedom, basically all the specific ways particles can vary or hold states. The number actually changes depending on the microscopic scale you're observing. Think of it kind of like a massive soundboard with different sliders. The number of available sliders changes depending on how closely you examine the system. The deeper you zoom in on reality, the more these categories splinter and reveal totally new ways of varying.
In 2011, Adam Schwimmer and Zohar Kamar-Gadowski proved a theorem defining the exact behavior of quantum fields in our 3+1-dimensional universe. This was a massive breakthrough. These two physicists calculated exactly how these effective degrees of freedom must behave as gravity tugs on them in our specific universe. A universe with 3 spatial dimensions and 1 dimension of time.
Their acclaimed math revealed a shocking truth about universal degrees of freedom. Quantum fields cannot just hold any arbitrary number of variations. They are locked into highly specific, rigid values. Scalar fields, like the Higgs, have exactly 1 degree of freedom. Force fields have 62. And matter fields, they have exactly 5.5 degrees of freedom. Yes, 5.5. This bizarre fractional dependency means that what's possible with one particle is actually partially dependent on the state of another. They are completely mathematically intertwined. To get the ultimate mathematically pure count, we can't just look at the universe today. We have to audit the primordial quantum fields exactly as they existed right at the Big Bang, before the Higgs field even gave everything mass. To find this number, we map out the initial 4 scalar fields, 45 fermion matter fields, and 12 force-carrying boson fields. We multiply them by those rigid new fractional rules, and we arrive at a truly staggering subtotal.
-95.5. When Komar-Gadowski fed these exact initial field figures into ChatGPT just to double-check his arithmetic, this was the staggering fractional reality of the standard model that it spit back out. If you count the fundamental degrees of freedom that make up our universe right at its birth, the ultimate answer is a fraction just shy of 1,000. Absolutely wild, right? 1, 5.5, 6, 2, they pop out of the theorem. I have no idea why this is what nature chose. Perhaps the most beautiful part of this entire discovery is this quote right here from Zohar Kamar-Gadowski himself. Even the brilliant theoretical physicists who discovered this theorem and proved it mathematically remained completely flummoxed by why our universe operates on these highly specific, rigid fractional values. It just goes to show that quantum field theory is unbelievably hard, and there is still so much we simply do not understand about the bedrock of our reality.
So, do you prefer the comfortable simplicity of 17 or the mysterious truth of 995.5? As we wrap up this explainer, I'm going to leave you to decide for yourself. When you look up at the universe, are you a minimalist who likes those 17 comfortable building blocks perfectly organized on a classroom poster? Or are you a maximalist, ready to embrace the tangled, fractional weirdness of a reality made up of 995.5 degrees of freedom? Whichever number you choose, it absolutely changes how you view the universe around you. So, what's your number?